Okay. Definition is a subset A of a topological space X is said to be closed if and only if the set X, the complement basically of A and X, is open. So starts to, now that we have some topological spaces, we can actually do some examples. If we have the closed interval AB as a subset of R, this is closed. Not because we call it a closed interval, but we can actually say we know why it's closed. It's because its complement in R, so R without the set A to B, is a union of minus infinity to A, non-inclusive with B up to, and so these are two open sets, and so their union is open. So another example is if we took this ray from A to infinity as a subset of R. This is also closed. Because if we were to take its complement in R, then we would get R minus A to infinity is just now down from minus infinity up to A, which is open in R. And then we also, but we get an interesting thing where it doesn't necessarily have to be either open or closed. So if I took not a full ray, but just from A to B where it's half like this, as a subset of R, this is neither open or nor closed. So the half open sets are fun. And we can extend this to R2 as well. We can do, so if I took a product of, so X cross Y with non-negative XY, this as a subset of R2 is also closed. Because if I'm to take R2 and take away these points X cross Y for non-negative XY, that's pretty much taking minus infinity up to 0 and then taking that cross with R, and then the union of all of these together with then doing R cross minus infinity to 0. This is a product of two open sets, and so it's open, and then their union is open. Okay. And then finite complement topology in the finite complement topology that we defined, I think, 2 weeks ago on a set X, then the closed sets consist of just X itself, because its complement would be empty, which is open, and all finite subsets of X.
So there are some sets that can be both open and closed at the same time.
Okay. Yeah. Okay. So then there's a theorem where.
So how does that go with the definition? Because if you have something that's both open and closed, is its complement both open and closed too? Okay.
I'm trying to think. There was one that it was, I think it's on R. I'm pretty sure. Oh. Because R is open on R, but R minus R, its complement. So its complement itself is open, which means it's closed. So R would be both open and closed with R. Because if I took R a subset of R, then it's closed because its complement R minus R, the empty set, is open in R. And then also the empty set would be
Closed.
both open and closed, because if I took the empty set from R and then took its complement, well, R minus empty is R, which is open.
Yeah.
So it bounces back and forth if you take the set with itself. So I don't think he names it, but he probably, some algebraist probably has made a definition for like a reflexively open and closed. The sets are trivially open and closed. Now let me erase this. There's a theorem for basically doing the definition of a topology, but with respect to the closed sets instead of the open sets. And then we can prove it. And then essentially, to go the other direction, it's analogous. So theorem, let X be a topological space then the following hold. So first things first is that the empty set and the set itself are closed. That's given definitionally. Second thing is that instead of it being it's flipped around. Instead of being arbitrary unions and finite intersections for the opens, it's going to be now arbitrary intersections and then the finite unions. So arbitrary intersections of closed sets are closed. And then the finite unions of closed sets are closed. Okay. And so proof for the first one here is just going to simply be, okay, well, if I take X minus empty, that's X, which is open. And then also I can take X minus X is empty, which is open. So they're both closed. And for 2, what we're going to do is we're going to first start with a collection of sets. So given a collection of closed sets, we can just index it over some indexing set J. We apply, and De Morgan's becomes useful. Which is essentially if I take the complement of the intersections, so alpha and J, A, alpha, then the complement of the intersections is going to be the union of the complements. So the union of each individual complement. However, we know that X minus A alpha is open by definition because we said that A alphas are closed.
Yeah.
So X minus A alpha is going to be open then. And since that's open, arbitrary unions of open sets is open. So then the union A alpha J X minus A alpha is also open, which means that the complement of this intersection ended up being open. So that gives what we want. The intersection
itself
is closed.
That's pretty cool. I like that.
Yeah. And then for 3, it's pretty similar. Is now instead of just doing an arbitrary thing, we're going to take a finite collection. So we can take, so if AI is closed for some I is 1 to n, So now it's finite. Now we're just going to consider another, it's basically De Morgan's again, but if I take the complement of this finite union from 1 to n of may I ai's, then the complement of the unions is going to be the intersection of the complements. So intersection of the complements. And again, the logic is exactly the same now because AI by hypothesis is closed, so its complement will be open, x minus AI open, which gives, and since this is open, and we have a finite intersection, x minus AI, that will be open as well. And then we have an open set, which is the complement of the union. So as we wanted to show, the union, the finite union of closed sets is closed.
Nice.
Cool.
Nice, isn't it?
So good exercise for De Morgan's.
Mm-hmm.
I'm pretty sure I've used that before a few weeks ago for something else. Can't remember what. Okay. So now it starts to get, we clarify some terminology because when we had subspaces, we had things being closed under a certain subspace. So distinguishing the terminology here is specifically, so definition, if Y is a subspace of X, we say that a set A is closed in the subspace Y if and only if the complement Y minus A is open in Y. So to distinguish that openness doesn't necessarily pertain to X. So it's only relating to the immediate set that it's a subset of.
Mm-hmm.
Okay, so theorem. Let Y be a subspace of X. Subspace of X. Then a set A. And set A is closed in Y if A is the intersection of a closed set, the closed set of X with Y. So if we have a closed set of X and we make an intersection with the subspace Y, and if A is that intersection, then A will be closed in Y. Yeah, so it'll go both ways. So we'll prove it both ways. So we're gonna do this version. We're gonna take the intersection and give that A is closed in Y. So we'll assume that we have A being the intersection of some C intersecting Y, where C is going to be open in X, or sorry, closed in X. Yeah, so where C is closed in X. So here's kind of a little visual that I process everything with. So here's X. And so I'm going to have A being an intersection. So I'm going to have some Y being the subspace, but then I have a closed set in X. So say something like this. And so A is then being this intersection in here. But I'm interested in obviously the complement X minus C. So if this is the closed set and this is my subspace, then it's going to be all of this stuff that's outside of C. star. So we have then the x minus c is open in X, but definitionally, so that the X minus C, that open set in X, intersecting with Y, which is just going to be this now, right? Is open in Y. Open in Y. And that's given by the subspace topology.
Okay.
So maybe I'll include what definition that is. So definitions of subspace topology.
So we need it to be a subspace.
Yeah. But, and then the visual helps here. So if I take the x minus c, that open set, so all of the lines that are slashed like that, if I am intersecting that with the subspace y, then it's going to essentially just be if I had started with y and then taken out a. So we're going to have that the x minus c open set intersecting with y is actually just the complement of a inside of y.
Yeah.
But we just said that this is open, which means that this is going to be equal. So y minus a is open in y, and that's going to then give that a is closed in y.
Good picture.
So yeah, this was helpful. And so now let's do the converse. So conversely, we're gonna now assume that a is closed in y and then give the complement open in y. So a, well, we gotta assume this. We don't start. So assume that a is closed in y. Then by definition, then y minus a, that complement, is open in y. And that's going to tell us that y without a, the complement, which is, and then here's a picture. So if I've got some topological space X, and then I've got another subspace of X, Y, but now I'm going to have some, I'm going to have an open set U of the topological space here. So I'll call this U, this will be open, and this will be A here. And so the complement X without U, since U is open, will be closed in X. So I'll put that in this dash outside here. And that actually does include the A. Okay. So Y without the A is we're intersecting this open set with the subspace. So the open set with the subspace is our Y without A, where U is open X. And so that's going to give that X without the open is closed in X by definition. But we have that A is going to be, if I take my subspace Y here, and if I intersect it with the complement of U with respect to X, I'm going to end up with this little piece in here. So I get Y intersecting the complement of U and X.
Clever.
And so then we can see that A is just the intersection of a closed set, which is why we originally chose U to be open. So of X plus Y.
Yeah, right.
So this one's a little bit trickier than this one, but putting the A there with choosing an open set.
Yeah.
Okay. I still can't tell whether topology, at least point set topology, how different it is, or if it's just taking set theory and putting it on steroids. Because so much of the logic comes down to being able to see the intersections and the complements. It makes me curious what next semester is going to be about for algebra. Okay. And then basically kind of it's not the same thing, but it's a related idea that you can then simplify. So it says that in special case, if Y is a subspace of X, and then if A is closed in Y, and Y closed in X, Y closed in X, then A is closed in X. There was a parallel theorem to that with the open sets earlier. Okay. So a definition is going to be given a subset A of a topological space I'm gonna call it X, the interior of A is defined as the union of all open sets contained in the subset. And the closure of A is defined as the intersection of all closed sets containing A.
Aha. Good.
Yeah. And then he has certain notation he's going to use where that's going to be interior of A, that's going to be the closure of A, or he'll use the subset with the bar over it for closure.
Does he have a symbol for interior?
No, he doesn't. The way he brushed it off was basically, well, interior sets aren't as important. And I was like, okay. I mean, I don't know any better. So
What I've seen is an A with a circle above it.
So like that.
That's the interior.
Okay, I've seen that before. I wasn't sure what that. Okay, so this is interiors and that's the closure of it. Okay, that's good. And then just for the sake of having it out, then interior is a subset of there, and then that's your closure. So in the event that I have A is an open subset of X, then A is actually just its interior.
Yeah.
It's the interior, and then if A is closed in X, then A will just be its closure. Okay. And so theorem, let Y be a subspace of X with a subset of A of Y, and then A is going to denote the closure of A and X. Then the closure of A in Y is closure of A intersecting with Y. So his point was basically you have to be careful when you talk about closure of a subset with respect to which one. So if you have a topological space A all the way to X, just because you have a subspace doesn't necessarily mean it's going to be the same closure. So distinguishing between he's reserving this closure for the entire topological space, and then using the intersection of the closure with whatever subspace you want to denote the closure of A inside of the subspace instead. So that was just a little technicality. And so definition is a set intersects a set B if and only if their intersection is not empty. So that terminology is going to be used to make things a little less wordy. So there's a theorem that uses that. So we have theorem. Let A be a subset of a topological space X. I actually had a question for you. I've seen this done before in a paper, and I really like it just because it's efficient. But is this a generally accepted way to communicate that A is a subset of X, which is a topological space?
Mhm.
That works? Okay.
Yeah.
Because I really like that, and I've seen some books do it, and then some that like will spell out both separate clauses. And
Right.
If this was nice, I'll use that.
So more advanced books will use the shortened version.
Okay. Probably after a certain point of redundancy
Yeah.
to keep saying it over and over again. Yeah. So the first thing is that if we have an element in the closure, that's true if and only if we take an intersection of U intersects A is not empty for all U X in U where U is open. So if I take a member of the closure, then that means essentially every single set that contains that particular element in the closure is going to intersect with A.
So every single open set that contains X intersect A can't be empty.
So like say you had 0 to 1, but the 0 is not inclusive.
Okay.
Then 0, if I wanted 0 in the closure, then that means every single open set in R that contains 0 will intersect with A. So they basically rename this horrific chunk of garbage into just a definition. They call it the neighborhood of
Yes.
X. Yeah. And that's where the other textbook that I saw last year would just skip right to the neighborhoods.
Open neighborhood.
Yeah.
Mm-hmm.
And then supposing the topology of X is given by a basis, and then X in the closure, and then it's the same construction really. So the basis element intersects for all the basis elements containing X.
It's just a special case.
Yeah, special case. And basically just makes a definition of the neighborhood here. So U is a neighbor neighborhood of an element X if and only if U is an open set containing X. Oh wait, that's the wrong X. Little X. And so, for example, if I took R, and then if I took the subset 0, 1, and then that lets me know that the closure is just going to be closing of 0 and 1. Because every neighborhood of 0 intersects A. They try to do this in R2 with circles. So they'll like draw, actually in regions in Calc 3 when we talk about interior exterior stuff. So they'll have like a region. And then this is interior because all of the neighborhoods will only contain points of R, or this is not because there will always exist an intersection between the region from that particular point. So this would be like an R2. The closure of positive integers is actually just positive integers. And then the closure of positive real numbers is the positive reals, and then in a very similar way to like why that would just go to closing to 0, we just close off the 0. And so this, I think I remember there was a notation, this notation was introduced earlier in an example when we had positives with 0. So, yeah, that's closed sets.
Have they talked about boundary points yet?
That's the next part. So he builds all this to construct in the next section the limit points, and then boundary stuff, and then I think it's like Hausdorff spaces.
Okay.
Yeah, so that's why I figured, ooh, that's gonna take more time to get there. But
Cool.
this was good. Yep.
I like it.
All right.
Okay, so next.